Hi, this is Tavi Greiner, Astronomy.FM's Vice President of Communications. If you enjoy our programming, please let us know with a donation to Astronomy.FM/donate. We really do rely on your support, and it's true, every little bit counts.
AFM.
The sun is yellow, Sirius is blue, and good grief, the sky is too. I like listening to the voice of the universe, Astronomy.FM radio.
Hello and welcome to another edition of Comet Watch. Hello and welcome to Comet Watch October. It's me and my trusty sidekick,
Mary McIntyre.
Neil can't be with us. He has laryngitis, poor boy. Absolutely bad and rotten luck. But never mind. Mary and I will get started when we'll do the gubbins. It's going to be time for the shipping forecast. So I'll kick us off with Warchalk Bloomplod reports a Kreutz Group comet in real-time C3 images.
And September the 15th, Warchalk Bloomplod reports a Kreutz Group comet in real-time C3 images.
September 18th, Masnora Yuchina reports a Kreutz Group comet in real-time C2 images.
September the 20th was the recovery of 2010 P4, periodic-wise, as 2017 S1.
September 22nd, discovery of 2017 R1 periodic pan-stars reported.
September the 22nd, discovery of 2017 S1 pan-stars reported.
September 22nd, Masnora Yuchina reports a Kreutz Group comet in real-time C3 images.
And September the 22nd again, Warchalk Bloomplod reports a Kreutz Group comet in real-time C3 images.
September the 25th, Warchalk Bloomplod reports a Kreutz Group comet in real-time C3 images.
September the 26th, and again, Warchalk Bloomplod reports a Kreutz Group comet in real-time C3 images.
September 26th, Zheng Hao reports a Kreutz Group comet in real-time C3 images. 27th of September, discovery of 2017 S3 pan-stars reported. September 28th, Igor Asayov reports a Kreutz Group comet in real-time C3 images.
September the 28th, discovery/recovery of 2017 S4 periodic Spacewatch reported.
September 29th, discovery of 2017 S5 periodic Atlas reported.
October the 3rd, Warchalk Bloomplod reports a Kreutz Group comet in real-time C3 images.
October the 4th, Sergei Surkopakov reports non-group comet in real-time C3 images.
October the 8th was the discovery of 2017 S6 Catalina reported.
October 8th, discovery of 2017 S7 Lemon reported.
October the 8th again, Masnora Yuchina reports a Kreutz Group comet in real-time C2 images.
October the 8th, Warchalk Bloomplod reports a Kreutz Group comet in real-time C3 images.
October the 8th, Warchalk Bloomplod reports another Kreutz Group comet in real-time C3 images.
And October the 9th was the update. Now, there has been no recent updates to the BAA Visual Observations page. Thank you, Nick. We really do appreciate the use of this. You can always try the German Comet Group or Salichi Yoshida's page for more information, or the Liga Ibero-Americana de Astronomía for observations. And now we continue with the shipping forecast. This is current comet magnitudes October 7th on observable region October 3rd. And this is the one comet I really hate at this minute. Assassin 2017-01, magnitude 8.5, is steady. 80 degrees north to 40 degrees south, best in the morning. Last visual observation was October 2017.
Then we have 24P Shao Mass, magnitude 11 and brightening. That's observable 65 degrees north to 15 degrees south, best visible in the morning, and the last reported observation was October 2017.
Johnson 27V2, magnitude 11, fading, 5 degrees north to 70 degrees south. It's an evening object, and the last visual observation was September 2017.
Then we have Pan-STARRS 2015 ER61, magnitude 12 and fading, observable 80 degrees north to 45 degrees south. That's best viewed in the morning. Last visual observation reported in September 2017.
17P Clark, magnitude 12, fade. It's 25 degrees north to 70 degrees south in the evening. Last observed August 2017.
217 periodic linear, that is magnitude 13 and fading, observable 65 degrees north to 40 degrees south, best observed in the morning, and that it was last observed in August 2017.
My old friend, 29p Schwachmann-Wachmann, 13 magnitude, question mark. It does vary, 50 degrees north to 70 degrees south, early evening. Last visually observed September 2017.
Pan-STARRS 2016 R2, that is currently 13.5 magnitude and brightening, observable 70 degrees north to 65 degrees south, visible in the morning, and the last visual observation for that was October 2017.
Lemon Yong, I believe that's Pan-S means Pan-STARRS 2015 VL62, 13.5, it's steady, 50 degrees north to 65 degrees south, early evening object, last visually observed August 2017.
And finally we have Pan-STARRS 2015 01, magnitude 14 and steady, observable 65 degrees north to 10 south, visible in the evening, and the last visual observation of that one was July 2017.
As always, the observable region is an approximate indication of the latitude at which the comet may be seen. Of course, under good conditions, comets may be visible outside this range. This is also the period when visible for the UK. If the comet is visible from the UK, otherwise or for 40 degrees south of the equator is approximate. Of course, last visual observation is as received by the BAA Comet section. Details are often dated on the basis of observations published elsewhere. Please always check your sources. Some are better than others, unfortunately. So, of course, the highlights obviously is 2017 01 Assassin, which is driving me totally and utterly mental, because every time I image it I get a nice streaky star field. I might get the NGC object, but no comet, even though I tried getting it before the moon rises. So I think I'm going to try and get it with another different robotic telescope provider, and hopefully I'll get lucky before it heads south.
Somebody was saying earlier on Facebook that they saw it in 10 by 50 binoculars last night, but it's the first time I've really seen anybody saying they can find it. It seems to be really diffuse.
Yeah, I know Neil said that he had seen it a few days ago in binoculars, and he said it was very diffuse and that, but that was even before moonrise. And of course, sometimes some of the scopes that I really want to use, the real big light buckets, I have to wait until 6 o'clock in the morning, my time, to get on them, and I'm imaging out of either Sierra Nevada or May Hill, New Mexico. So I'm going to probably wait until this little one goes south and hopefully pick it up via the SSO. Well, that was the shipping forecast, and I know that if you're currently living in the UK, you're getting a very different shipping forecast, because you've got Hurricane Ophelia on your doorstep. So good luck, everybody. Hunker down and good luck, and you'll get through it. So time to have our guests introduce themselves.
All right, hi. I'm Rick Hill. I'm formerly with the Catalina Sky Survey, currently retired, and found my comets with the survey.
Debating on who to jump in with. This is Jim Scotti. I'm at the Spacewatch project, also at the Lunar and Planetary Lab. I helped start these guys about 20 years ago or more.
And our final guest is...
And my name is Richard Kowalski. I'm also at the Lunar and Planetary Laboratory in Tucson with the Catalina Sky Survey.
Welcome back, guys. It is nice to have you all on the same show. I don't think we've actually done that yet. I think this is the first time.
Thank you. It's good to be back.
It's fun.
Now,
yep, good to be here.
I've got a few ideas to talk about, but I think we'll just do it as pitch questions in and let you guys discuss them, because I think the last time we did that was just the perfect show, everybody said. So let's start with what are your views on the current crop of comets?
Well, Assassin is quite an interesting name. There's a little bit of controversy over the group's name. with the IAU. They weren't sure if they wanted to allow the name of the comet to go through, or at least someone on the nomenclature committee wasn't sure about it.
What was their reason for that?
I think they were a little concerned that the way it's pronounced is assassin, and there's some concern that the public, some elements of the public are concerned about impactors, and that we wouldn't talk about an impactor that's on its way in, even though it would be public knowledge. So there's just a little concern that it just was not an appropriate name for a comet, even though it's an acronym.
Yeah. I have to worry what would they thought if the group had called themselves Ninja. I could just imagine the reaction to that one.
Well, the press think the world's going to end every month at the moment anyway, so I personally don't think it makes any difference, but...
No.
Well, at least I have a few friends, and I'm sure Rick and Jim have as well, who take these the world is coming to an end by asteroid or comet stories with a grain of salt, and quite often they'll ask me if there's any validity to it. And of course, there never is, for the most part.
Well, Rich, you're the only person alive right now who's discovered an asteroid that actually hit the Earth after you discovered it, so we got to watch out for whatever you discover.
That's true. He's found two that hit the Earth.
Yeah.
Yeah, that's a point, yeah.
It is a cool job, isn't it?
Absolutely.
Yeah, definitely.
It was great.
You know what? Since it's always thought, we know for a fact that a comet ended the dinosaurs. Why don't we discuss stuff like Spacewatch? Because I'm pretty sure that's on a lot of people's mind. How does something like Spacewatch function around the world? Can you guys help with that?
Well, Spacewatch is our group. Space Guard is what the sort of global network might have been called. Unlike most of the science fiction stories, Armageddon or Deep Impact, we're not going to be able to hide an impending impact. Once we find an object, it's in the public domain. Everybody can look at all the information. They can compute their own orbits with software that works almost as well as what the Minor Planet Center can use, and it'll be there, and it might be inbound, and it might be a couple of days, like in the case of Rich's two asteroids that hit the Earth. They hit fairly soon after discovery, but luckily they were all very small, and a really big one would probably be discovered weeks ahead of time. So I also like to think of Shoemaker-Levy 9 as a really good example of something that could hit the Earth, because that was a comet, or a comet-like object anyway, and we had about 15 months warning before it hit Jupiter. So all those Jovian dinosaurs, I guess, were wiped out back then. So
I have to admit, Shoemaker-Levy 9, I don't want to say I enjoyed it. I did enjoy the whole thing, because it really brought the Astro community together, I think, on the project. I think everybody did something and committed resources, from either confirmation work, because I know that some of you guys got mentioned repeatedly in David's book about the whole thing.
Yep.
So it shows that there is actually a consensus and a desire to actually do the science and perhaps look at these things. Yes, watching the actual impacts on Jupiter was fascinating.
Yeah, and it took almost 2 months before we figured out that it was going to hit Jupiter. So that, I think, represents how long it might take for us to find out that some asteroid or comet was inbound and going to hit the Earth after it was discovered. So, it's different parts of the problem, I think, were well demonstrated there, as well as some of the side effects of the impact as well. So,
So one question I have about that other listeners might be wondering is, in terms of the time difference in discovering it versus when it's going to potentially impact, does this difference in time, is it down to the size of the object, or is it down to its brightness, the albedo of it? Or is it a combination of both?
Probably a little bit of each. An object that's very far away from the Earth would have to be bigger to be discovered in the first place, and it would also take longer, I think, for you to figure out that it was going to hit the Earth. An object that's small and nearby, you can use parallax and things like that, and within hours you might be able to tell that it was going to hit the Earth, like Rich's objects did. Or the Chelyabinsk object would have been an example. If we could have seen it before impact, it would have been seen in the hours before impact, not weeks or months. But that was a small object too, so a lot of different problems to solve in that case, and you never know what it's going to be until you actually see it.
So presumably the limiting magnitude is getting fainter and fainter as the equipment gets better.
To some extent, I think my Catalina friends have more or less caught up to where we were about 15 or 20 years ago, at least in terms of magnitude. They can cover a whole lot more sky than we ever did back then, so that's why they're way more successful at asteroid discoveries than we were, although we were one of only a couple of groups doing it back when we started, so we got the ball rolling down the hill.
Now, you've all discovered comets. How do you report it? How do you work the sky?
Well,
go ahead, Rich.
Okay, I'll take it. With Catalina Sky Survey, we're taking images of regions of the sky. We have standard fields that we program the telescope to observe with regularity. The program will observe each field 4 times over the period of about 30 to 40 minutes, and the software then compares what is in each image. The background stars, of course, are not moving in relationship, so we can pick out the objects that are asteroids and comets. It typically takes a minute or two for us to validate each field and to tell if the detections that the software is coming up with are real or not, or known or not. The entire process then to report a new NEO or a comet is essentially the same for us. Once we've determined that it is not a known comet, we then submit our astrometric observations to the Minor Planet Center and include the title in the subject line that it's a comet candidate, and we also add a few additional addresses to the distribution, and typically we'll put a short description into the comment lines. If we notice a tail, how long it is, what the position angle is, what the diameter of the coma is, if it's bright and condensed or faint and diffuse, those types of descriptors. And that entire process between our validating it as real, checking to see if it's known, and then submitting the observations typically takes less than 5 minutes. And quite often the Minor Planet Center's checks, once they get our email, will only take about 5 or 10 minutes as well. So new NEOs and new comets quite often go up on the NEO confirmation page for confirmation within about 10 or 15 minutes of discovery. It's a very rapid process.
Oh, it's really fast, isn't it?
And it's important to point out that the description of the tail, the coma, and things like that are what's important. You cannot call it based on motion.
Yeah, you forgot to mention the minute or two that you spend jumping up and down after you checked for other comets and realized, oh, it's a new one. No one else has found it yet. Yay!
You come across a comet at 3 in the morning, and I guarantee you're good to go till sunrise. It's a real adrenaline jolt.
two of you work for Catalina, and
I work for Spacewatch.
Yeah. So I'm just because so how do you interact? Do you interact when you get for a confirmation or anything?
I think we all interact through the Near Earth Object Confirmation page.
Right.
We rarely ever call the other observatory. I think we can probably count that on one hand how many times we've called them to help with something. Generally, there's a really good network around the world through the confirmation page for confirming asteroids and comets. It works really well.
And when I was there was a blog as well. I don't think that works anymore. I think the blog is gone.
And with Catalina Sky Survey, we now have a 1 meter remotely operated follow-up telescope. It's station I-52, and whichever observer is assigned to that, typically they're working here on campus down in the valley, not up on the mountain, and they're constantly monitoring the confirmation page for new discoveries. And as soon as a new object is discovered, either by our program or by Pan-STARRS or even amateur stations, we will then put that into our observing queue, and typically that brand discovery, no matter who's discovered it, will be observed by a Catalina telescope, typically within about an hour of discovery.
Now, if my memory serves me right, and sometimes it does, I know that, particularly with Shoemaker Levy 9, that they had problems with the film. Someone had actually opened their film drawer and light damaged them, so they were actually just using up films at the time. And as I remember, Jim, you were asked to do the confirmation on that one, weren't you?
Right, yeah. It was sort of late afternoon when I got an email, and while I was reading the email, I got a phone call from my friend David Levy, and they were still on Mount Palomar, and Carolyn Shoemaker had just recently found the images, and it was cloudy there. They were in a sort of messy night, I think, when they took the Discovery films. But it was clear on Kitt Peak, although we were a day away from getting the same clouds they saw. And the object didn't rise until quite a bit later, so it was close to midnight, I think, by the time I actually observed the comet. I got them worried, though, because when they described it and mentioned that it was moving at like the same rate as Jupiter, and it was pretty close to Jupiter. Mm-hmm. I said, well, are you sure it's not a reflection in the telescope from Jupiter? I had them really worried. So they went back and looked at their films, and as soon as I saw the first indication of a comet in my scan that night, I knew that their object was real, because we don't get the same reflections in our optics as they would get in theirs. And all I saw at first was what looked like a faint, long tail. And then I saw a second little tail. And then I saw what made my jaw drop for the rest of the night, the long string of little nuclei. And
pearls,
other tails, And then there was the second tail going the other, or the third tail, I should say, going the other direction. And it was just, wow. And it wasn't too long after that David called me and said, well. He says, I said, boy, do you have a comet? I can't remember what I said. I was jumping up and down so much, I think, oh, look at this. We've never seen anything like that before. And I remember talking to Gene Shoemaker that night, and because it was so close to Jupiter, we were talking about, well, maybe it just flew past Jupiter and got shattered into pieces. We didn't expect it to come back and hit Jupiter the next year. And that didn't come out until I think about 2 or 3 months later, when its orbit was solidified and its impact the following July was predicted. So that was a really exciting time of my career. One of the highlights, definitely.
Yeah, you weren't getting a lot of sleep either, because I was in the computer lab the next day at LPL, and you called me over to a computer that morning and showed me the images.
Yeah.
I have to admit, one of the things I know he said was that they had often wondered about this line of craters that's seen on one of Jupiter's moons. And
Callisto.
Callisto, yeah. And could it have actually been another comet that Jupiter had smashed up? And instead of impacting Jupiter, it just impacted on Callisto instead, giving us a very unusual formation. I don't think there's really much... I can't remember anything really like that on the Moon at all. No, I could be wrong.
Yes, actually, there are a few. Yeah. After I came back from Kitt Peak observing, one of the first people I went to at the lab was Jay Malash, who I knew was interested in binary impact craters and things like that. And he dragged me back to his office and said, "Oh yeah, that image I saw, because it had already been in the newspaper, I think. It reminded me of these craters we saw on Callisto during Voyager that we had no explanation for." So he dug out a picture of one of these crater chains, and it's like, well, I think we have an answer for what happened here now. None of the craters on Callisto, like some of the crater chains on the Moon, some of those point back to primary impact craters, much larger impact craters. But the ones on Callisto didn't do that.
Of skim along. So the primary ones would kind of skim along the surface to produce multiple craters, whereas the others have a slightly different shape. Is that right?
Yeah, the Callisto chains were, like tens of little discrete craters all lined up in a row, slightly different in size and stuff. While the ones on the Moon, I think you get sort of debris flying out, like you say, sort of low angles and stuff like that.
Catena Davy over near Ptolemais on the Moon is thought to be a primary impact crater chain.
Yeah?
Yeah.
That'd give that an area an eyeball then. Because I've... reading that book, it really... Well, it made me think about a lot of stuff because it meant that we'd missed a smoking gun ourselves. If it had happened to Callisto, and this kind of looks like it's happened to our Moon, what had happened if the Earth had actually been in that particular spot at the right time or wrong time? It would have been the Earth that got the nice little row of damage.
And we probably did.
Yeah.
Yeah.
We probably did, but we have weather, and that erases things.
Yep, and of course plate tectonics doesn't help either.
Yep.
And most likely one of those, could have happened, or quite a few of those could have happened a long, long time ago when impact rates were higher during the late heavy bombardment and things like that. So it's definitely, different than what it would be at Jupiter as well. So
exactly.
Of course, the flip side of the Jupiter impacts was the fact that it gave us an idea of the atmosphere as well, because we were looking at the signatures, spectrometry signatures. Now, again, correct me if I'm wrong, because I haven't read the book in about 7 months. But we could actually see not only the makeup of the cometary gases, we could also see the Jovian signatures as well.
Yeah, I don't remember the details of that, but that's definitely a side effect of getting to see that. Galileo saw the impacts from partway there, so it got to look around the edge a little bit better, whereas things like Hubble Space Telescope was limited to the Earth view, and the impacts were just around the corner and rotated into view fairly quickly, so we actually did get to see things pretty clearly. And in fact, I remember thinking I was disappointed when they first predicted where the impacts were going to be, because it was going to be around the edge where you couldn't see them. But it turns out that was almost a perfect place to see what was going on from Earth, because moments after the impact, this huge cloud exploded over the horizon where we could see it against the black sky, and then within an hour it rotated into the field of view where we could see the impact site itself too. So it really worked out pretty well.
And one of the other exciting things about the SL9 impacts, it was the first time through the internet that astronomers all over the world could actually share in the event happening live. And that was really exciting for us back at LPL, who weren't on a telescope at the time.
Yeah,
Well,
I don't
yes.
think I was aware of just at such a high-profile pro-am collaboration type thing going on before that happened. I don't know if I'm wrong, but I don't remember hearing about it in quite the same way that, like you said, the whole astronomy community came together with that one, didn't they? And backing everyone up, and yeah.
We were in computer labs all over LPL watching the feed coming in live and seeing these impacts. It was terrific. It was wonderful.
I was out in the Negev Desert in Israel at the WISE Observatory, and we were connected to the universe by something like 1,200 baud. So I didn't get to see the images that night right after discovery, or right after the first impacts.
Did you have to turn a crank on the side of the computer in order to get the...
Yeah, just to get the bits to process, yeah. So I was trying to observe the nuclei as late as possible before they impacted, and my observing plans didn't work out too well, and we couldn't see them, and we were hoping to see maybe flashes off the moon. We had some amateurs looking through telescopes, and from my point of view, it was almost a failure that we hadn't really seen anything. And then the next morning after I got up, we had a newspaper with pictures of the impacts from Hubble, and it was like, oh, wow. That made the rest of my week. Yeah, we were there for more than a week for those impacts. It was a lot of fun.
So in a way, SL9 set the scene for today's modern pro-am collaborations, really, like we have going on with a lot of the current comets.
I would say so. It also will Congress up and many other scientific disciplines to the fact that there are still impacts occurring in the solar system today. Before that, there was what was known as a giggle factor, where some planetary scientists said there are still impacts occurring, but most people just laughed it off. And that event convinced many other scientists, as well as Congress, that yes, this is a legitimate concern and we should be looking for impactors ourselves.
Not only that, but we were surprised by the impacts. Even the small bodies had more energy in the impact than we thought we were going to see. And that made us rethink Earth impacts, potential Earth impacts.
And of course, we still get them going on today. We got blindsided by Tablinsk. We were looking in the wrong direction. But and yet they seem to be. Well, the Australians lost their survey. Rob McNaught, I think, had to go home in the end because there was nothing for him to do, which was sad, really, because he was doing some really sterling work as well. Out of the Siding Springs Observatory. I'm going to explain quickly. When I mention SSO, I mean Siding Springs Observatory. Sometimes it's quicker just to say it that way.
It's a pity that Rob was shut down too, because right now there is no survey watching the deep southern sky, and Chelyabinsk type objects can sneak in from that region.
Well, what compounds the loss of the Siding Springs survey, what makes it worse is that they were using Catalina Sky Survey equipment. They were using our software and one of our cameras, and the offer was made by our then principal investigator to leave the equipment in Australia as long as they would make some NEO observations once a lunation. The terms were so generous for Australia to at least have some semblance of at least a follow-up program, and there was absolutely no interest in Australia at all to pay Rob to maintain any part of the survey. It was very sad. So the equipment was all shipped back to the U.S., and it's now in storage.
Yeah. So sad.
Very
there are
sad.
There are a couple of observers in New Zealand that do some comet observations, I suppose asteroid observations as well. Alan Gilmore and Pam Kilmartin, they were inspirations to me and when I first got into comets. as comet observers down there, and they use the Mount John Observatory in New Zealand, as I recall.
Yes, I've heard about the Mount John. I think Rodney mentioned that a few times when we spoke to him that time as well. Maybe it's time for Catalina to expand south and maybe set up a survey in conjunction with local university or something. If they've only got to make an observation, a certain amount of observations during a given lunaration, I would have thought it would have been very easy for a university to task a pair of students who have been suitably trained to run the equipment and to report the data.
Well, the deal at that time was for Australia to do it essentially at Siding Spring, in essence to help keep Rob employed as well, because he was, as we've already mentioned, a great observer and did a fantastic job finding comets too. But they just didn't want to spend the money on his salary, and that's the primary cost of the funding would have been for Rob's salary, and they didn't want to cover it.
A great loss, and of course it may be a great loss to the whole of mankind one of these days.
Exactly.
But the good thing is, though, okay, in the Northern Hemisphere, we are still going one of the 10 great guns at surveying. There's a survey team down in South America, Gustavo. He's got his own Sonia observatory running, and I believe he's actually, in some respects, doing it in a very similar way to Catalina.
It could be. I'm not exactly sure how he's doing it, though.
From what I understand, he's got 2 telescopes mounted, and he's looking in those in the places close to the horizon where Linnea and Catalina don't normally go. That's where he's finding his comets a lot of the time.
You mean closer to the sun?
Probably close to the sun, but he said that when we interviewed him, he said that he looks in there's that little space that where the major surveys don't go for some reason, but he goes into that and
far to the south.
Oh, right. Well, amateurs, when I give talks, amateurs ask me, where can we look for comets anymore? And I generally tell them north of plus 70 degrees and inside of a 60-degree elongation from the sun. And that's pretty wide open right now. Is that what you're talking about?
Yeah, that's probably what I am talking about. I just remember him say he didn't give me an exact figures and where he looked, but he was looking in that one place where most of the surveys don't go. And
south of minus 30 or 40 degrees declination as well.
And he's finding stuff there, and I think he's got 3 or 4 comets to his name now, purely in that little sweet zone that nobody else looks at.
Mm-hmm.
Well, the traditional locations for sweeping up comets near sun after sunset and near sun before sunrise are still prime locations.
Absolutely.
We're changing our procedures a little bit at Catalina. We're now doing a bit more of programmed surveying where the software determines where we're going to observe. And near sun, both evening and dawn, are wide open for anyone that wants to look for comets.
Well,
are the telescopes used on the surveys a standard model that everyone's kind of chosen, or does every observatory have a different setup?
Rich and I are chuckling because one of the brilliant moves of Steve Larson, who was one of the founders of Catalina Sky Survey, was to use existing telescopes, refurbish them, in some cases replacing the optics, and get them back in service. They were derelict telescopes. And so one's a Schmidt, one's a modified new Cassegrain, and what's the I-52 is what, a Dahl-Kirkham?
Something like that, yeah.
So they're all different. We use whatever we could get. Does that give you a problem
then? I was going to say, does that give you a problem when people are trying to do follow-up observations?
No, because the observations have to be reported. The accuracy of the positions have to be, 0.2 arc seconds, I believe. So, yeah, we have to report to the same accuracy that everybody else would.
Well, one of the things that we've done is we've essentially written nearly all of our own software, and it's deployed through all three telescopes. So we have the two survey telescopes have the same camera and thermoelectric cooling system. The software is the same for all three telescopes. So there are only minor differences between each telescope, but an observer sitting down at one telescope can do the job at any of them.
Right.
And also, the software and the equipment is constantly evolving and improving. Each month they learn from the previous month's problems, and then they make changes and upgrades from there. In the 2 years I've been gone, I think it's changed so much I'd have to be retrained if I were to go back.
Probably. There have definitely been a number of changes since you retired.
Even to the cameras. The cameras are twice as big now.
Yeah.
So what kind of cameras are you using at the Catalina and at Spacewatch?
Well, at Catalina, we have cameras that are built by a company here in Tucson called Spectral Instruments, and both of them have 100-megapixel chips in them.
Wow.
Wow. Just imagine one of those in be turning up to an astronomy meeting with a telescope and saying, "This is my new camera. It's a 100-megapixel chip."
Isn't it true, Rich, that the camera on the 60-inch, you can cover the entire dipper of the Big Dipper's bowl? You can cover the entire dipper in 4 frames?
I believe so, yes.
Down to 21st magnitude in 30 seconds.
In 30 seconds, yeah.
That's incredible.
That's
why they... Go ahead, Rick.
That's why they find all the rocks.
It's a 1.5-meter telescope f2. So
f2? Wow.
Photographers know that's a really fast light gathering system.
Now, Jim, you're using the one that's got one of the old MMT mirrors, aren't you?
Yeah, we have 2 telescopes on Kitt Peak that we use. We use the old 36-inch telescope, which is actually the oldest telescope on Kitt Peak. It was originally built in Tucson on the U of A campus and moved up in the early 1960s to Kitt Peak. When we took it over in the early 1980s, it was not being used except by, I think, grad students doing their pet projects. So we got full use of it. And then in the late 1990s, we built our 1.8-meter telescope, which uses one of the mirrors that was in the MMT a long time ago, the multiple mirror telescope, which used to be 6 1.8-meter mirrors. And they actually had, I think, 7 mirrors they used, one spare that they could rotate into service while they worked on other ones. But one of those mirrors was actually Tom Garrell's mirror that he had gotten back in the 1960s. And it just took him a long time before he got the funding to build a telescope around the mirror. We, in 2001 to 2003, we built a new camera for the 36-inch, which is a mosaic camera. And I'd have to stop and think about how many pixels it actually has, but it's 4 2x4K chips butted together. And that had been used for surveying from 2003 until about 2 years ago when we started switching it into follow-up mode. So we're only doing follow-up now, and any discoveries we make from now on will be incidental to follow-up, which we're always still on the lookout. Any image you take of the night sky that is as big as that, it's 2.7 arc or degrees across. Anyway, any of those images are potentially populated with interesting objects. Comets, I don't mind discovering, for example, and near-Earth asteroids and things like that. So we're on the lookout for those, even though our primary goal, of course, is to find a specific asteroid that we're going after. We've actually doubled our follow-up rate because the 36-inch is a lot easier. We spend less time on a target. We go after slightly brighter targets with that telescope than we do with the 1.8 meter. The 1.8 meter uses a camera that any of you guys can buy if you're rich enough. It's a Finger Lakes camera, 2K by 2K, that has about a 20 arc-minute field of view. And that works pretty well for our follow-up. We can read out a lot faster, but we tend to sit on fainter targets for longer, so we'll end up with 35 or 40 targets on the 36-inch on a night and only 20 or 25 on the 1.8 meter, even though we could go after the same targets on the 1.8 meter and finish them a lot faster if we were going after the brighter stuff. But anyway, we keep busy, obviously.
Now, a lot of these images are available publicly, so if you want to spend your evening poring over the images that's been taken by the surveys, they're available for public consumption, correct?
Ours aren't. They were for a while. We had a program in the early 2000s called the FMO project that put the data available online for anyone to log in and download images and look for the long-trailed images of fast-moving objects. The observers didn't have time to do that kind of thing while observing, but that project took a person, more or less a full-time job down back at the lab to keep up with all the detections or false alarms or whatever else they had to cover. So our data are not readily available. We are making an archive available to go back and use the data if you need to maybe look for an object that might have been observed by us at some point. But that's still coming online. I'm not sure. How are you guys doing at Catalina?
Archiving's a big problem because I think CSS is probably approaching a petabyte worth of images by now. And you're talking about a major project to have that all available, say, through a website or FTP site.
Hey, guys, can I ask a favour? Can I stop the show for about 20 minutes so I can go and quickly... Okay, we had a short break due to technical issues. So now can you guys tell us about these new cameras?
Well, the Catalina Sky Survey. Sorry, I'm stumbling over my words here. We have recently upgraded the cameras in our survey telescopes, the 1.5 meter up on Mount Lemmon and the 0.9 meter on 0.8 meter on Mount Bigelow. It's a Schmidt camera. Both of these cameras are made by, as I said earlier, a company here in Tucson called Spectral Instruments. And they both have monolithic chips that are 10K by 10K pixels on a side, or 100 million pixels. The camera in the 1.5 meter, which is an F2 system, covers 2 degrees on a side. So we are recording 4 square degrees down to 21st magnitude in a 30-second exposure.
Wow.
That's deep. That's going very, very deep.
It is, but most of these objects that we're looking for, as Jim was explaining earlier, they tend to be smaller and less bright. We detect the larger ones because they tend to be a bit brighter further away, but these small ones we don't catch until they get close enough and bright enough. A big part of the strategy for looking for near-Earth asteroids and comets is to cover a lot of sky and go as deep as you can, as quickly as you can.
Have you had any chance to do any comet imaging with these new cameras?
Nothing specifically yet.
I always used to do my focus tests on comets.
That's a good idea. I'm going to have to try that one.
That way I killed 2 birds with 1 stone.
But this comet is out of focus. I can't focus on it.
Yeah, there you go.
It's fuzzy.
So what are your expectations from all the new equipment?
The name of the game, like I said, is covering as much sky as possible. And previously we were hoping to cover much of the visible sky from our site with the Schmidt telescope, 1.5, maybe if we could get it done twice per lunation. And with the 1.5 meter, because the field of view was only 1 square degree with our old cameras, we tended to stay near opposition point and along the ecliptic. And our expectation now with this new camera is we should be able to cover the observable sky each lunation to the 21st magnitude with our 1.5 meter and cover the entire visible sky with the Schmidt camera possibly 3 times every lunation. So that's at least for the Schmidt a 50% increase, and for the 60 many time increase.
So roughly how many pictures a night do you think you take?
Well, it's dependent on the amount of time we have each night, and of course the nights in December are a lot longer than the nights in June.
Yeah.
In the winter, we're hoping to take approximately 600 images per night, 600 to 700 per night.
Okay, so presumably they're quite big file sizes with those cameras, so you're going to have how do you tackle the issues with data storage?
Well, currently we are using a non-lossy compression algorithm, and we are burning our data to 100 gigabyte Blu-ray discs. And
right.
Some nights it takes more than 100 gigabytes to store that compressed data. We're also transmitting the data down to our archival machines in the lab in real time as well. So once it goes through the process, a copy is sent down to the archive machine on campus, and then we make another optical copy at the telescopes each morning.
Right. You're going to end up rivaling the square kilometre array with your data at this rate.
Oh, I hope not.
The thing is, with all these telescopes and Pan-STARRS and Spacewatch, we're catching comets now. I think we're seeing comets more often. We're finding them when the comet gets discovered. We're finding pre-discovery images, but there's no cometary details. We're catching them before they turn on, before they develop a tail, before they develop a coma. And that's kind of the name of the game now, anywhere except those 2 regions we talked about earlier.
Yeah, there's a object that has been, it's a main belt comet that Hubble just recently observed to be a binary comet. And it turns out I was the discoverer of it back in 2006.
Oh,
and,
really?
It was sort of, wow, really? So I went back and looked at the images from 2006, and it's completely stellar, but of course it was 21st magnitude then too, so it's not exactly easy to see much activity there. But we observed it a few years later when it was recognized as a comet, and it has a nice long narrow tail. It's maybe an arc minute long.
That's what happened to me with P2013R3, the one that broke up. Hubble imaged it breaking up. I found that asteroid. It was next to a bad column of pixels and a bright star, so the tail wasn't visible at the time. It would have been the best object I ever found. And later on, Pan-STARRS found that it did have a tail, and Steve Larson got some time on Hubble, and it's all history from there.
Yeah.
But
this comet I mentioned was actually in what we called the incidental astrometry. It was never actually looked at by me that night. Most of our asteroid discoveries in those days would just go out in a list of positions, 3 positions per object, and only the ones that had interesting motion would be presented to the observer to examine, or if it was detected as being fuzzy, we would be presented with it as well. So I never saw that. It just went out in the morning mail like it normally would. And I never even had a chance to see if it was commentary on that particular night back in 2006. So interesting way to, how can you look at 4,000 or 5,000 objects a night?
That's one of the problems is so many objects are discovered by each telescope every night. You can't look at them all. You can only look at the stuff that's interesting.
Yeah.
And you've got to set some parameters, and maybe some of that comes back to bite you later, but you do the best you can,
As long as it doesn't come down on our heads, we're okay, though.
That's right. That's exactly it.
Yeah, our survey strategy with the 36-inch and the Mosaic camera was to revisit each region of the sky near opposition that we surveyed 4 or 5 times during illumination. And that way you would observe the background main-built asteroids, and hopefully maybe the occasional near-Earth asteroid that would have slightly different motion but not different enough to be called out, that you could link them up. The Minor Planet Center would link them all up with their software to look for matching objects or observations of the same objects. And we managed to get 100,000 or so main-built asteroid discoveries that way, just by linking up all the incidental detections of all the main-built asteroids that are in the background of all the things we're looking at.
And one of the things I've been seeing is that we're finding that some asteroids are growing tails as well, which was never previously.
I was going to just say that. I was going to mention that.
Go for it.
That's been one of the fascinating things. Steve Larson started that at CSS with 596 Sheila, 596 Sheila, back in 2010 when he found it had a tail. And our software identified the asteroids, the known asteroids, put the name right above them when we find them. And here came up with the name Sheila on it, and it had a tail. And he followed it up, and he got the first one.
That must have been a really interesting day to suddenly discover that an object you tagged as an asteroid is now suddenly a comet. But they seem to be flying slowly now.
That's what happened with 2013 R3. It went from an asteroid, and then they found a tail on it, and so they listed it as a comet. Then it went back to an asteroid that was breaking up and just had a lot of dust. And so it went back and forth between asteroid and comet as characterization.
Well, I've always found the difference between comets and asteroids being a little bit fuzzy. Sorry.
You got to watch out. You don't want to get us all together, because this goes on and on.
Hey,
all of us.
Well, it just turns into a long tail.
Well, that's the thing about comets. Some of them do have long tails.
All these puns will put you in a coma, I'm telling you.
Or you'll have the cat nervous.
Saving these up.
No, we've used them for years.
Okay.
Well, David,
Remember I said Rick was old earlier? He's got a lot of old jokes, too.
Hey, I started in astronomy in 1957, so...
Oh dear! Because I know most people have started seeing the comet puns coming out with David Levy and his cat analogy about how comet tails behaves. But hey, great! Bring them on, gentlemen! Bring them on. If anything,
I always thought David wanted to own a catadioptic telescope.
Mm-hmm.
You could really see all the tails.
Yeah. I think this is probably the thing I enjoy about having you guys on the show, because there is the humour as well. And I don't think many people realise what a humorous group astronomers can get, even with the good puns, the bad puns, and the downright
Especially
ugly ones.
This is what comes of being in the dark all night, looking at little tiny pinpoints of light.
Mm-hmm.
We're very sad people, I guess.
Mine can only take so much.
That's it.
Well, guys, I'm going to have to say this has been apart from some of the technical issues we've had this afternoon, this evening. It's afternoon for you, it's evening for me, and it's late night for Mary. But this for me is one of the reasons I like doing this show, because I get three people on like you guys. We get the humour flowing. We get some really great stuff that most people don't realise about places like Spacewatch, about Catalina. Most people just equate them with their function. That's it. They don't get to hear about how things are done, the fun, the games, the humour. So I think most people say, "Oh, well, it's another Catalina rock, or it's another Catalina Comet," but they just don't realise what goes into finding these things and some of the humour that gets generated or regenerated
or degenerated.
Yeah, I'll wait for that one. Well, I think this is probably a good point to wind up the show. I'm really grateful for you to come. I'm really sad that Neil couldn't have been part of it, because I think he would have been rolling around the floor laughing himself silly. But this has been a great show, guys. I think we're going to have to do this again. Hopefully,
it was great fun.
The Skype gremlins will not appear next time. But there's plenty of stuff I think we can discuss, and I know that given half the chance, we'd be on here for the next 5 hours still discussing stuff.
Definitely.
Yeah.
So
it works better with some beers.
Hey, tell you what, I've got an idea. We'll get a recorder, a digital recorder. We'll all get together. We'll get some beer in, and then we'll record the show.
Rich knows a couple of good places too.
I think that's the nice thing. That's some.
It could be. We could do another show called Comet Watch: The Extended Tales. We all have a beer and chat afterwards.
Now you're getting in the spirit.
Yeah.
You're getting in the envelope of the whole thing.
Oh yeah. It's a very.
You guys are going to be pretty fuzzy if you drink too many beers, though.
Oh yeah.
Oh yeah. I'll bring some of my real ale for you guys as well. We'll all be fuzzy by then.
There you go.
You'd be fuzzy if you drank my rhubarb gin that I've just made, that's for sure.
That sounds good. We have to get you guys over to the UK or get Mary over here with some of her rhubarb gin, or I'll make some rhubarb gin, so she doesn't get nicked by customs and excise coming into the country. We'll sit around, we'll actually have a...
We'll all go wind the Harrison clocks then.
Oh, yes.
Ooh, that sounds like fun.
So I think just remains to actually say our good nights and say,
all right,
Rick, Jim, Rich, brilliant having you back. Fun and games, and I wouldn't have missed this for the world. So it's good night from me.
Good night from me.
Thanks for having us.
From Tucson.
And look up. I can't.
And get well soon, Neil, as well.
Yeah, get well soon. We miss you, Neil. Good night, guys. Thank you very much for coming
Bye.
on.
Bye-bye.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of Astronomy.FM. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are Astronomy.FM. You may also find us in the iTunes radio listings near the top of the News Talk section, and also as an iTunes podcast selection. We'd love to hear your comments. Please email us at radio@astronomy.fm. Thanks so much for being part of the voice of astronomy around the world and across the known universe. This is Astronomy.FM Radio.
Hi, this is Tavi Greiner, Astronomy.FM's Vice President of Communications. If you enjoy our programming, please let us know with a donation to Astronomy.FM/donate. We really do rely on your support, and it's true, every little bit counts.
AFM